Short-circuit forces. Introduction. The sizes of generators and transformers, along with the voltage of the transmission line, have steadily increased since the commercialization of electrical power to meet the ever-increasing demand. Networks at all levels of voltages are linked to make them rigid and reliable. The consequence of such a trend has resulted in ever-increasing fault levels on buses at generation, transmission, and distribution voltages. Disruption due to a short-circuit fault in a network can have disastrous consequences leading to loss of life, property, and revenue. All electrical equipment had to keep pace with their ability to withstand increasing fault levels. The impact has been most felt in the switchgear and busbar systems. Containing the increasing thermal, dielectric and electrodynamic stresses on electrical equipment in the industry has been a challenge. The three-phase, short-circuit current at some of the locations in the network are as detailed in Table 7.1. Continuous current rating of AC induction and arc furnace and DC metal extraction plants have also seen a phenomenal increase. Short-circuit forces are an important parameter in the development and design of busbar systems. Forces. A current-carrying conductor produces a magnetic field. Another conductor in its vicinity carrying current will also produce a magnetic field. Their interaction will result in the conductors experiencing a force. In a busbar system, rigid conductors, or for that matter, strung conductors in a transmission line or switchyard, run parallel to each other and will experience a force depending upon the magnitude and relative direction of the currents in the conductors and the spacing between them. If the currents in the two conductors that run parallel are in the same direction, there will be a force of attraction. If they run in opposite directions, then they will experience a force of repulsion. Two conductors running parallel, separated by a distance d and carrying go and return alternating current of magnitude I, will experience a repulsive force. This force will be repulsive and unidirectional but will vibrate at twice the system frequency. In the case of a single-phase AC go and return system, the currents in the two conductors will always be out of phase at 180 degrees. The force will be in the plane of the conductor and will be repulsive. The conductor will vibrate at twice the system frequency. When a fault occurs on a single-phase line, the short-circuit currents will be much larger than the rated current. The power factor of the fault current will depend on the impedance behind the fault. The fault current wave, more often than not, will not be symmetrical. It depends on the point on a wave at which the fault occurs and the power factor of the line. On an unloaded line, the current has to start from zero and reach a maximum during its first peak. This offset in the current wave can best be analyzed by superimposing symmetrical phase alternating current on a decaying direct current. The degree of asymmetry will depend upon the magnitude of the direct current. The peak value will depend upon the impedance and the power factor. The maximum peak will correspond to zero power factor reaching a theoretical maximum of 2.828 and the minimum at unity power factor at 1.414. The decay time from peak asymmetry to symmetry will depend upon the time constant dictated by the ratio of inductance to resistance, LR, of the conductor. The multiplication factor for the peak current, for the other power factors, is given in the table 7.2. For analysis, this asymmetrical waveform can be split into two components comprising a decaying direct current and symmetrical alternating current. In a two-conductor, single-phase circuit, the magnitude and shape of the waveform will be identical but in the opposite direction. The resultant force will be the superimposition of four components comprising DC component of conductor A interacting with the DC component of conductor B. The force will be repulsive, unidirectional, and decaying with time. DC component of conductor A interacting with the AC component of conductor B. The force will be oscillating at system frequency and decaying with time. AC component of conductor A interacting with the DC component of conductor B. The force will be oscillating at system frequency and decaying with time. AC component of conductor A interacting with the AC component of conductor B. The force will be repulsive and oscillating at double the system frequency. Once the DC component has decayed significantly, the contribution from the first three components of the forces can be neglected and the force on conductors will oscillate at double the system frequency. Three conductors in line formation. Conductor in the middle will experience the maximum momentary force irrespective of the occurrence of a fault on any of the phases on the point on a wave for the maximum force. Conductor in the middle will experience the maximum steady-state force, oscillating at twice the system frequency. The force will be bidirectional and linear. Conductors in the extreme ends will experience equal and opposite steady-state force oscillating at twice the system frequency. The force will be almost unidirectional, and its amplitude will be almost half that of the force on the conductor in the middle. 3 conductors in-line formation. Distortion in the amplitude of the waveform will significantly reduce at the end of the time constant. For a line-to-line fault on an unloaded line, the waveform will be similar to that of a fault on a single-phase go and return circuit. The analogy will hold good even for a lightly loaded line or when the ratio of the fault current to load current is significantly high. Section modulus of the conductor subjected to the oscillating force remains constant, therefore the stress and deflection will be proportional to the force. 3 conductors in-line formation. Figure 7.5 details the amplitude and direction of the force. Since the section modulus remains the same, it also represents the amplitude and direction of the stress and deflection. Insulators can be oriented and located strategically to offer the maximum factor of safety. 3 conductors in delta formation. The conductor carrying the maximum fault current will experience the maximum momentary force. For a line-to-line fault on an unloaded line, the waveform will be similar to that of a fault on a single-phase, go and return circuit. The analogy will hold good even for a lightly loaded line or when the ratio of the fault current to load current is significantly high. The force experienced by the conductor will be oscillatory. The steady-state short-circuit forces experienced by the conductor will be identical because of the symmetrical nature of the configuration. 3 conductors in delta formation. The conductor carrying the maximum fault current will experience the maximum momentary force. All conductors will experience an equal steady-state rotary force, rotating at twice the system frequency. The direction of rotation will depend upon the phase sequence. The distortion in the amplitude of the waveform will significantly reduce at the end of the time constant. The steady-state short-circuit forces experienced by the conductor will be identical because of the symmetrical nature of the configuration. 3 conductors in delta formation. All conductors will experience an equal steady-state rotary force, rotating at twice the system frequency. The direction of rotation will depend upon the phase sequence. The distortion in the amplitude of the waveform will significantly reduce at the end of the time constant. For tubular conductors, the section modulus will be the same along any radial axis and therefore the stress and deflection will be proportional to the force within the elastic limits. For cross-sections other than circular, the section modulus of the conductor will vary along the plane of the direction of the force. Consequently, the deflection caused by the force will not be proportional to the magnitude of the force. Maximum stress and deflection need to be evaluated for the actual orientation of the conductor. Stress and deflection arrived at based on maximum force and minimum section modulus will be very conservative. The insulator and conductor clamping arrangements need to be designed and strategically located to restrain the conductor, subjected to a rotary force, with the desired factor of safety. The steady-state short-circuit forces experienced by the conductor will be identical because of the symmetrical nature of the configuration. Proximity effect. The formulae have been derived for solid round conductors, the cross-section represented by a point. The analysis is valid for round conductors where the diameter is significantly less than the spacing separating the neighboring conductors, as in the case of tubular rods or conductors in high-voltage switchyards. In low and medium voltage applications, the shape and configuration are far removed from these ideal conditions. Consider the examples of 2 conductors carrying current in the same direction and the opposite direction. The proximity effect tends to distort the current density distribution. The effective distance, considering the center of gravity of the current density, will be different from the geometric distance between the center of the cylinders. It will depend upon the proximity and the direction of the flow of the current. The current density will move in a direction that will result in the least inductance, while the force will act in a direction that will increase the stored inductance energy. Proximity effect. As has been detailed elsewhere, the proximity effect tends to alter the effective distance between the conductors, and this has to be factored in when the force is evaluated. It is noticed that when the currents are in the same direction, the effective distance increases, and therefore the force of attraction gets reduced from the ideal condition. However, when the currents are in opposite directions, the effective distance decreases, and the force of repulsion gets increased from the ideal condition. A similar phenomenon will occur when the 3 conductors in a 3-phase system are placed either in line or in delta formation. The effective distance will change with the magnitude and relative directions of the current. Stresses. When a short circuit takes place, forces are generated uniformly along the length of the conductor. The conductors are bolted or clamped onto insulators. The insulator, in turn, is bolted to the supporting member. It is the normal practice to provide a cushion in the interface between the conductor and insulator, or insulator and supporting member, or both. When the force acts on the conductor, it will yield. Fiber stress must be limited to a value within the yield stress, with a safety margin, to prevent the conductor from experiencing permanent deformation. In a busbar system, the conductor is supported or clamped by many insulators along its length. A conductor supported on 2 insulators, 1 span, can be approximated to a simply supported beam, whereas if it is supported with 3 or more insulators, 2 spans or more, then it can be approximated to a continuous beam. Stresses. Short-circuit generated electrodynamic force on the busbars is considered to be a uniformly loaded beam with multiple supports. For the solutions to such a problem, the theorem of 3 moments is applied. It can be established that the bending moment, fiber stress, and deflection arrived at above for a simply supported beam are higher than those for a continuous beam. The reaction at the supports of a continuous beam is higher than that for a simply supported beam. For a 3-support beam with 2 spans, the reaction in the middle support is 25% more for the continuous beam than that for a simply supported beam. The maximum internal moment and reaction force occurs when the beam is supported on 3 insulators. The reactions and bending moments are detailed in Table 7.5. Deflection and resonance. A conductor supported by a set of insulators at reasonably regular intervals will deflect on the application of a force. On a short circuit, the force will have an oscillating frequency corresponding to the system frequency and double the system frequency. Any beam supported at its end will have a natural frequency of vibration which is based on its moment of inertia, span, and modulus of elasticity. As a thumb rule for any given structure, the natural frequency of vibration, in cycles per second, as a function of deflection delta, in millimeters is given by the equation. Frequency equals a constant k divided by square root of delta. K equals 18 when the deflection is expressed in mm and 3.52 when expressed in inches. It is necessary to ensure that the natural frequency of vibration does not resonate with the forced vibration induced by the short-circuit forces. For a given geometric shape and material of busbar, the only variable parameter to control the natural frequency is the span, which should be designed to avoid resonance. Following thumb rule may be followed to stay clear of resonant conditions. For a system frequency of 50 cycles per second, avoid a range of natural frequency from 40 to 60 and 80 to 120 cycles per second. For a system frequency of 60 cycles per second, avoid a range of natural frequency from 50 to 70 and 110 to 130 cycles per second. For outdoor tubular conductors installed in the switchyard, wind loads result in a vertical oscillation due to the formation and shedding of a vortex. These are termed as aeolian oscillations. These occur when the wind speeds are generally less than 7 meters per second. These oscillations have been recorded with a frequency between 5 to 150 cycles per second. The amplitude is small and limited to the diameter of the conductor, and the plane of vibration is perpendicular to the plane of the direction of the wind. Such vibrations can result in fatigue failure. Larger wind speeds are too turbulent to induce vibration. All profiles of conductors will vibrate in the presence of streamlined low wind speeds, when the span is long enough to vibrate, when the wind energy is more than the losses in support. Long spans are preferred in open yards to reduce the number of supports and thereby obtain a more economical design. Natural frequency should not resonate with aeolian oscillation frequency. In a high-voltage open switchyard, since the phase spacing is large, the electrodynamic forces due to the short circuit are marginal. Apart from the aeolian vibrations, transmission line conductors are sometimes subjected to a very low frequency of oscillation, closer to 1 cycle per second, with a very significant amplitude of the approximate order of a meter, 3 feet. These are termed as conductor dancing or conductor galloping. Uneven ice loading may be the cause of such a phenomenon. These can be controlled by suitable dampers and spacers. Short-circuit current waveform. The magnitude and asymmetry of a short-circuit current waveform in a network will depend upon several factors. The discussions are limited to its effect on the electrodynamic forces. Type of fault. The fault in a three-phase system can be categorized as line to ground, line to line, double line to ground, triple line, and triple line to ground fault. The magnitude of the steady-state fault current will depend upon the equivalent source voltage and combined series impedance through which the fault current flows. Line-to-ground faults are most common in any network. In a low-voltage system, the voltage across the arc can be significant compared to the rated voltage, and consequently, the fault current will be much lower than a prospective fault current with a bolted earth connection. For medium and high-voltage systems, the voltage across the arc is of little significance. In a network, a line-to-ground fault can result in a double line-to-ground or even a triple line-to-ground fault due to the dispersion of ionized air. Load before fault. In most of the situations, the magnitude of the fault current will be far more than the load current before the occurrence of the fault. The magnitude and power factor of the load will have only a marginal impact on the DC component of the fault current. Point on wave of occurrence of a fault. The instant of the occurrence of the fault on a wave will determine the magnitude of the DC component of the current. Fault location and source impedance. The fault can occur in any location of the network comprising generators, transformers, line, overhead and cables at different voltages, and other series elements such as reactors. The intensity of the fault current will depend upon the voltage and impedance of the upstream elements, including the source impedance rationalized on a unit system. From the viewpoint of the nature of fault current waveform, the locations can be classified as those that are farther away from the generator and those that are near a generator. Fault away from the generator. This is a condition where the series impedance between the generator terminals and the location of the fault is significantly higher than the generator impedance. Let a sinusoidal source having an R, M, S value, E, be switched on to a load, Z, having a power factor phi. Since the instantaneous current has to be zero at time t equals 0, it will generate a DC component that will decay exponentially with a time constant defined by the circuit parameter ratio of inductance to resistance. The DC component will depend upon the power factor and the point on the wave at the instant of connection. Let the connection, fault, be initiated at an instant when the voltage wave has a magnitude corresponding to an angle alpha. The waveform will be symmetrical when alpha and phi are equal to 90 degrees. The waveform will have the maximum asymmetry when alpha is equal to 0 and phi is equal to 90 degrees. Fault near the generator. This is a condition where the fault occurs in the very close proximity of the generator terminals. A connection between the generator and generator transformer has several tap-offs to feed auxiliaries through auxiliary transformers, to static excitation system, and to surge protection, voltage transformer cubicles. Any fault on the terminal equipment at the generation voltage will fall under this category. The shape of the waveform shown in figure 7.1 will depend upon sub-transient, transient, steady-state reactance and respective time constants. Generator terminals are connected to the step-up transformer by a metal-enclosed, air-insulated busbar system. These are isolated phase bus for large capacity units and segregated phase bus for smaller units. These connections incorporate current transformers and generator circuit breakers if specified. The magnetic parameters of the current transformers will depend upon the magnitude of the asymmetry of the current waveform. The zero crossing of the instantaneous value of current may take more than a cycle depending upon the generator parameters. Consequently, the arcing time of generator circuit breaker may be long. As discussed earlier, a fault current in a three-phase AC network is transient in nature until it is cleared by a protective device such as a circuit breaker. The current waveform comprises a decaying DC and an AC component will eventually stabilize, a symmetrical wave, before being isolated from the faulty network. For a fault at a location far removed from the generator, the AC component of the fault current will be constant and DC component of the fault current will decay with a fixed time constant. However, for a fault close to the generator, the AC component of the fault current will decrease in magnitude and stabilize while the DC component of the fault current will decay with a varying time constant. For the maximum asymmetrical current, the peak value obtained in the first quarter of the cycle shall be considered. Thank you. Mr. Balachandran graduated with a bachelor's degree, B.Tech, in electrical engineering from the Indian Institute of Technology, Madras, India, in 1967, and obtained a master's degree, M.E., in power engineering from the Indian Institute of Science, Bangalore, India, in 1970. He is a Fellow of the Institution of Engineers, FIE-India, Fellow of Institution of Engineering Technology and Chartered Engineer, FIET-UK, and Life Senior Member of the Institution of Electrical and Electronics Engineers, IEEE-US. He was the founder director of Power Gear Limited and Busbar Systems, India Limited. He has worked in manufacturing industries in India and the UK and is currently an advisor. He has engineered several busbar systems that have been manufactured and installed in various countries, including isolated phase bus for the largest hydroelectric power plant, 26 by 800 megawatts, at the Three Gorges project in China. During his professional career, he has developed and tested a range of bus products and their accessories. His area of interest also includes switchgear, instrument transformers, and power system analysis. The book, An Introduction to Busbar Systems, authored by V. Balachandran, is case-bound, hardcover, size A4, 386 pages, printed on 100 GSM glossy paper. Copies of the book can be purchased with a requisition to Bala at busbarsystems.net. Black and white version of the book is for sale in India, Afghanistan, Bangladesh, Bhutan, Nepal, Pakistan, and Sri Lanka at a cost of 4,500 Indian rupees plus freight. Color version of the book is for sale in all other countries at a cost of US $126.00 plus freight.